Okay, so we're going to talk about logarithmic functions. And so there's a little picture of me saying, what? Um, so a log, and this is me saying, what? And then this is Mr. Krause, because he's a nerd. Look at that. Look at his buck teeth. Nerd. Nerd. Okay. A logarithm is a number x in the exponent by which the base has to be raised to produce the number y. Huh? Logarithm of a number. So logarithm, we call it log, of a number x is equals the exponent by which the base has to be raised. So you know how with exponentials we have the form y equals ab to the x? The base of a log goes as a subscript on the log. So we'll show you on the calculator in just a minute. So what I want you to have in your brain is that logarithm is exponent. And that should help when you're writing things down. Because log, that's easy, is means equals, and then the exponent. So first thing we're going to do here is we're going to, we have a graph of 10 to the x on the grid. And on the same set of axes, we're going to graph regular log, or log base 10, because that's our common base. We talked about that the other day. We're going to graph that on the calculator. So in the calculator, what you want to do is you want to go to your graph, and then above the 10 in blue here, but yellow on yours, so control log, you get this notation. Our base is 10 because it's a common log, and we're typing in x. So you can see this little graph. Now I'm also going to graph just because I'm a crazy person. I just want to show you something. 10 to the x, so we can see both of them on there. Beautiful. And I'm just going to do this. Hold on. I'm going to say this is from -4 to -4 to 10 to 10, just like on our graph. So now I'm going to go to the table. Control T. And our log function points that we're going to graph are right there. So let's go here. Log of 0, we can see, is hashtag undefined. So let's write that down. So undefined. You don't have to write the hashtag. I'm just being a booger right now. Then 1 is 0. 4 is our next good point. So 4 is 0.602. And when we're graphing, it's easiest to do nearest tenth because hundredth and all of that really is not helpful to our lives. So then we go down here, we get 0.778, so I'm going to go with 0.8. And then 8 is 0.9, and 10 is 1. So 8 is 0.9, and 10 is 1. All right, so now if we actually want to graph this, the undefined is giving us dead giveaway that there is an asymptote here. Asymptote at x equals 0, which coincidentally is the y-axis. So there is an asymptote there. We draw them as dotted. So we have 1, 0, 4.6, 6.8, 8.9, and 10, 1. So you see how creepily slow it is. Now, over here it's going to come down, make sure it doesn't cross that asymptote, and then here it just creeps up real slow like. So this is g of x, and then this one was f of x. Okay, beautiful. So it says determine the following characteristics. What transformation turns f into g? Well, I'm hoping that you can see, and we've talked about it quite often, you can see that that would be a reflection through the line y equals x. So what is their relationship? So it switches the x and y. That's my hint. The relationship then is that they're inverses. Whoa! Okay. So the domain of the log is can't be equal to 0, but then it goes up to infinity. So 0 to infinity. The range, it goes all the way down to negative infinity and up to infinity. The x-intercept we saw was at x equals 1. And the asymptote was x equals 0. Is the graph always increasing or decreasing? It's always increasing. Okay, so there's our graph of logs. So, just like with every graph that we talk about their characteristics, okay? For h, we have a base of 2. So this is what we call base 2. For j of x, that base is e. So we have an abbreviation for it, ln, meaning natural logarithm. And then with base 10, which we know is the common base, so this is called the common log, we don't write the base 10 if it's base 10 because it's to be understood, kind of like when we don't write an exponent of 1 or when we don't write the 2 on a square root. It's just understood to be there. So if you look at these graphs, you can notice that this is increasing the whole time. This is increasing, but not quite as fast. And this is increasing, but much slower. So what does changing the value of b, or making b bigger? Remember, e is approximately 2.71. So as we make b bigger, what happens to the graph? Yeah, it slows down. Okay. Write the equation of h inverse and j inverse of x. So we saw on the front that the inverse, g inverse of x, would be 10 to the x. So h inverse of x the 10 from here, the base of 10 came from the subscript. So we have a base of 2 to the x. J inverse of x. J inverse is the natural log, which means its base is e. So e to the x. So you are going to go here and you're going to write the inverses of each of these. Okay? So you have the exponential form and then the log form. So you have to be able to switch between log with a base of x to its inverse of b to the x. Take a second and do that. So this is an exponential. So its inverse is a log. So we have log base of 3 x. If you want to put parentheses around the x, that'd be good too. So 4 is an exponential, so its inverse is a logarithm. So f inverse of x equals log with a base of 5 of x. Number 5 is an exponential, so its inverse is a log with a base of a half, and x in the inside of the log. Now in the other direction, we're starting with something that's a log, so its inverse is an exponential. This has a base of 6, so 6 to the x. Number 7 is a logarithm, so its inverse is an exponential with base 4. Number 8 is a logarithm to start with a base of 13, so its inverse is an exponential with a base of 13. Quick and easy. So now the next part is like everything that's fabulous in your life, because now this is the 7th time we've talked about these transformations. So reflection in the x-axis is the negative. Dilation of A is that. This is left or right. This is up or down. I feel like at this point I don't have to show you the directions there. So, using your knowledge of transformations on other functions, determine what transformations were applied to the parent function f of x to obtain the function g of x. Thing you need to know, and it says state the asymptote of g. Thing you need to know is the asymptote of all of these begins as x equals 0. Gosh, spelling is hard right now. So let's think about this for a second. If I reflect over the x-axis, does my asymptote change? No. If you dilate, does your asymptote change? No. If you move left and right, so if we think about this graph like this, if we move this left and right, will the asymptote change? Yes. So this is going to affect the asymptote. Up and down isn't going to change it either because it's a vertical line, so it's not going to move. So let's talk about transformations and asymptotes. We start with regular natural log of x, which has a base e, by the way. Natural log, base e. So g of x, you can see the negative, which means a reflection in the x-axis. Plus 2 on the outside means goes up 2. Since there was no horizontal move, the asymptote remains x equals 0. Number 10, log base 2 of x. Now we have a 1/2 log base 2 of x plus 1. So the 1/2 outside is a dilation of a half. Inside, we're going to the left 1, which means our asymptote moves to be x equals -1. Number 11, we have log with no base written, which you have to know is base 10 if it's not written. So we have 2 out front, which means a dilation of 2. And we have -3 after the parentheses of the log. So that means we go down 3. Since we didn't go left or right at all, our asymptote is still x equals 0. Okay. Number 12, again, natural log, base e. You have to know that. So the 3 is a dilation of 3. -2 is to the right 2. -4 is down 4. So the moving right 2 changed our asymptote to x equals +2. Number 13, I see 2 transformations. Don't you try to tell me just one. Don't you dare. I will find you. All right, you know that the negative and the 3/4 are separate. So a reflection in the x-axis is from the negative, and a dilation of 3/4 is from the 3/4. Now, because we didn't have a translation to the left or right, our asymptote remains x equals 0. And this last one, there's no base for the log written, so we know it's a common base which is 10. Negative means reflection in the x-axis. Plus 10 inside means goes to the left 10. Plus 5 on the outside means goes up 5. So our vertical asymptote moves left 10, so x equals negative 10. All right, so here's what you want to do. Look at you being fancy. First of all, down here at the bottom, you have a list of functions. You are going to match them with the graph and just write the function in the graph. So like you'll write, f of x or g of x in these little bubbles. Take a second and do that. This should be the easy part. Okay, so this is putting all of our graphing things together, which is evil or awesome. I don't know which. Okay, so actually what I'm going to do right now is I'm going to go down here, and anything that's logarithmic, we can kind of pick out the asymptote, right? So for k of x, we should have an asymptote of x equals 3. For L of x, we should have an asymptote at x equals negative 2. And for g of x, we should have an asymptote of x equals negative 4. Those are vertical asymptotes. So let's see. Where do I see a vertical asymptote of 3 or negative 2 or negative 4? So negative 4, no. Negative 2, no. Negative 4, no. Negative 2, no. Negative 4, nope. Negative 2, nope. Okay. But this looks like it might have an asymptote at 3, yeah? At x equals positive 3. I guess that's k of x used. Okay. So now I'm looking around again. I can't really tell. This looks like 1, 2, 3, oh, this might be an asymptote of x equals negative 4. Yeah? So that looks like it's g of x. And now I can't really tell, but maybe at negative 2 here, that looks like x equals negative 2 is an asymptote, and it's flipped upside down. Yes? So that's L of x. Beautiful. So now what I'm going to remind you of is your exponential asymptotes. For an exponential function, the asymptote is the vertical shift. So y equals 2, y equals 2, and y equals negative 4. So those are horizontal asymptotes. So let's see. This looks like y equals 2. This looks like y equals 2. And this looks like an asymptote of y equals negative 4. So this must be j of x. My calculator could confirm all of this. But then the other two, let's see. They're both negative. One has a dilation of 2. The other has a dilation of 4. And one is moved to the right 3, and the other is not. Ah, okay. So doesn't this look like it moved to the right 3? So this must be f of x. And this must be, what is it, h of x? Oh gosh, Mr. Johnson is yelling all of the wrestling things right now. Okay, so like I said, you could confirm all of these with your calculator. So here's the big deal before we do the easy stuff. Write the equation of the new function and describe the transformations that occurred. This is what we call composing functions or evaluating functions with algebraic expressions. And we have done this in pretty much every unit, but it's not in your top 5 skills. So we're trying to get it at least in the top 15. Mr. Hertwick would appreciate it when you come to pre-calc if you could compose 2 functions. So we're going to try our best. So let's see here. I'm going to use green. We're starting with n of x is 2e to the x. Fine. M of x is n of negative x plus 3. So what I'm going to do is I'm going to figure out what the expression for n of negative x is. Now, if you listen to the words that I'm saying and you do it this way, this will be easier. And then when you go to Mr. Herwick's class, he won't shout at you. Actually, I might be lying. He might shout at you anyway. Okay. So what you want to do is you know that you're taking out x and you're replacing it with something. So anytime you make a substitution in math, you need to use parentheses. So you're going to remove the x. Just taking them out, digging out the hole, dig out the dirt. Okay, that x is the dirt. Now you're going to plant a new flower in there. Look at that. Negative x is your new flower. Everywhere you put a parenthesis. Ta-da! Okay, that's n of negative x. So m of x is n of negative x, 2e to the negative x, plus 3. It's over! That's it. That wasn't hard. Okay, let's try another one. This one, p of x is ln of x, which has a natural base of e minus 4. Find the equation q of x is 1/2 p of x minus 2. Well, let's go over here and figure out what p of x minus 2 is. So p, remove the x. So digging out the dirt. Leave parentheses in its place. You don't want the dirt to fill back in and collapse. You're going to put brand new flour in there. So now in there, you're going to put x minus 2 in all of the holes that you dug. Yay! Surprise! So now you can write q of x. Q of x is 1/2 of this. Parentheses, ln x minus 2 minus 4. Which we would probably rewrite as 1/2 ln x minus 2. That goes there, and then it goes, whoa, goes there. Sorry. It's over. Okay. One more crazy one. Now you got to be extra, Miss Newman. Well, I don't know how to be any other way. R of x plus 3. Okay. So we're replacing x. So dig it out. Dig it out. And you're replacing that with x plus 3. I don't know why I wrote so small. Holy smokes. All right, x plus 3 goes in those spots. Ooh. Now let's clean this up a little bit, because can you see what happens there? X plus 3 minus 3. So those are going to go whoosh. So r of x plus 3 is negative 2 e to the x plus 2. T of x equals negative 1/2 r of x plus 3, we just figured out, minus 2. Negative 1/2 times negative 2 is 1, e to the x. Negative 1/2 times positive 2 is negative 1, minus another 2. So final answer is e to the x minus 3. My Apple Watch just told me to breathe. Apparently I held my breath in that one. Okay, so that's evaluating. Now, regression. Do you know how to do this? Yes. Is it one of your top 5 skills? Yes. Is this a little bit weird? No. You just have to know how to read. Do you know how to read? Oh, good. Good plan. The table below shows the number of new stores in a Chipotle chain that opened during the years 2006 to 2014. So it gives you the year, the number of new stores. Fine. Using x equals 1 to represent the year 2006. The next person that doesn't read that and comes to me and says, my calculator gave me that answer, I'm going to say to them, do you know how to read? Because I know you do, but you just chose not to. 2006 becomes 1. 2007 is 2. 2008 is 3. 2009 is 4. and 5 and 6 and 7 and 8 and 9. Renumber that. And y to represent the number of new stores, write the exponential regression for these data. Round all values to the nearest thousandth. That's 3 decimals, so you need to look at the fourth, and it tells you to stay or raise. So let's go to the fancy calculator. You go to your spreadsheet, which is in the home screen. If there's anything else other than 1.1, then you click the red X and you do not save and you try again. So X and Y, 1, 2, 3, 4, 5, 6, 7, 8. I think we go to 9. I don't remember. Can't see. 14, 27, 48. Okay, so you put in all your data, and then you go to Menu, Statistics, Stat Calculations. We've done linear. We have done quadratic and cubic and quartic and power, but now, finally, we finally made it. Congratulations to exponential regression. What did we call our X list? Well, we called it X because we don't have a hard time. What did we call our Y list? Y, tab, tab, tab. Okay. It calculates for you. A star B caret X. If you write that, that means you don't understand what star and caret mean. You know that that stands for, first of all, it's an equation. Y equals A times B to the X. A, we said we need 3 decimal places, so we look at the fourth. So that says 10.5959. 5959. 5959 rounds up to 6. B, 1.5862. The 2 tells me to stay at 586. That is what we consider your work because it came out of your calculator, and you cannot turn your calculator in at the end of an exam. That is not a thing. We do not press print from the calculator. I need to see your work. Y equals 10.596. Parentheses. 1.586 to the X. Using your equation, determine which year Chipotle will have opened 2,000 stores. Well, 2,000 is the number of stores. So it's 2,000 equals this. And I haven't taught you how to solve that yet. So you never taught us this. Aha, you're right, I didn't. But you know what you do have is a calculator. So according to our model, we're going to go here. We're going to go to our graph. And we're going to type in our function 10.596, 1.586 to the X. We're going to graph that. And we're also going to graph 2,000. We're finding where these two things are equal, also known as we're finding where they intersect, which means I have to change what I see here. So up here, I'm going to go to like 2,500. Oops. 2,500. Okay, and clearly I can't see where they intersect, so I'm going to tab over here. Our table goes to 9 years, so I'm going to go to 20 years. See if that works. Oh, yep, it does. Enter. So where they intersect, menu, analyze the graph, intersection, click, click. In 11.36 years. Okay. So 11.36, X equals 11.36 years. But it says what year? So add 2006 to that, yes? So plus 2006. would be 2017.36. Now, so if you're 0.36 of a way through the year, aren't you in 2017? Yeah. So during 2017. Cool. All right, now, a logarithmic model. Let's clear all our things here. Doc B, go to our spreadsheet, click the red X, don't save. Okay, go back to the spreadsheet. We're going to create a logarithmic regression. Now this one is a little bit weird, so hold on to your seats here. So a savings account has a balance of $500. The number of years T that the money must be in the account for it to grow to a balance B dollars is shown in the accompanying table. Why does this not make sense to me? Okay, so I read it wrong, so that's why it didn't make sense. Got it. So it has a balance of $5. The number of years T that the money must be in the account for it to grow to a balance of B dollars. So really what we're saying is that B is the independent variable, and we want to know how time depends on the balance. I want to know when a certain balance, not after a certain amount of time. So we're going to use a logarithmic regression. So same idea, you're going to go to your calculator, you're going to do X and Y. You could do B and T, that's fine, but I would do X and Y just so you have a system here. Okay, so again, once you enter the data, you go to Menu, Statistics, Stat Calculations, and you won't see what you want. You're like, wait, where's logarithmic regression? Hold on. It's right after exponential. You see that? So choose logarithmic. X list we called X. Whoops. Y list we called Y. Tab, 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 all of the tabs. Okay. Now, look, arrow down to that equation. Look at the form of that equation. It says regression equation is A plus B ln of X. Y equals A plus B times the ln of X. ln has a base of E, which is the natural base, so we call it the natural log. A equals, and it says nearest hundredth, so negative 12, or negative 124, sorry. And I can't see what, oh, cancel. Negative 124.249. The 9 tells me to raise to 25. B, I go to there, it says 19.992. So stay at 19.99. But I want to, shh, don't do it. Y equals negative 124.25 plus 19.99 natural log of X. Use the regression equation to predict to the nearest tenth of a year the number of years the money must be left in the account for it to grow to a balance of 7,500. Now, hold on. Balance is what we called X. Years is what we called Y. True? So, we have a balance of 7,500. So, we're plugging that in for X. So, Y equals negative 124.25 plus 19.99 ln of 7,500. So let's go to our calculator and look at that. So you have to show that substitution for full credit. Otherwise, you're not going to get full credit. So make sure you're showing all formulas and substitutions. If I could type this, that'd be great. All formulas and substitutions that are appropriate for this situation. Now, ln is Control E button. Okay, so then we get 54.1139. It says to the number of years to the nearest tenth. There we go. 54.1139 is 54.1 years. Fabulous. All right, so your homework should be pretty straightforward. It follows the notes pretty closely. Make sure you do a nice job with 9, 10, and 11. You really want to focus on making sure you remove the x and then replace it with what is being subbed in the parentheses. On the back side, you are constructing scatter plots, so make sure you have a good scale. Make sure your axes are in an appropriate location. If you have only positive numbers and you put them in the center, you're not paying attention. If you have positives and negatives, you have to think about where the axes should go to make the most appropriate graph. Remember that scatter plot doesn't mean connect the dots. You're just plotting the information and then you're calculating the regression with a little screenshot that I provided you with.